am I doing today now? It's not going. Okay, it's not recording. Basically, this is the laptop update. Slide share. Wait, slide stuff. I love slide stuff. Basically, slide stuff really has a lot of information. But you gotta verify it. What you gotta do. Just recording my voice. It's flowing, and I can see it. Okay. Leptons by Jonathan Sargent. So I'm gonna refer this thing. Leptons are subatomic particles. They have a spin of half. Leptons are a family of fermions. Basically, this is scientific symbology. Leptons do not experience the strong force, but do respond to electromagnetic forces, weak forces, and gravitational forces. Okay. Basically, this is my take on it. But I will go slide open so I have to do it properly. There are 6 rows of electrons, electron, muons, tor. But the 6, because you get the inverse one. So there are 6 different types of leptons in the presentation, in the present structure. Leptons are subatomic particles. Very important. They're only subatomic. They only work in the subatomic world. That's obviously they're working on the field itself. They don't really you have to basically change your rotation. You have to rotate. You don't to get a measurement. If you change the measurement, you can't literally just observe an electron because nothing there to observe for you because you're not so to move. You have to be at the atomic structure to start observing electrons. Basically, you have to be at the nanoscale. Very important at the quantum level. You have to be. Why am I studying physics, Namdi? I'm studying physics because this is where I'm studying. Leptons are important because they are energy. They represent everything and nothing at the same time. But there's mostly nothing because they want to be nothing. That's why leptons really matter. Nothing of everything. Nothing in an absolute way of everything. They don't want to be relative to anything. But leptons are relative because they are part of the whole system. They are what do you call it? Anti-leptons. You get anti-leptons, which are the opposite of leptons, like can hold. Basically, leptons are nothing because they propagate as waves. But can be massed from. They also have spin. That's just leptons always a form of fermions. Leptons do not experience a strong force, but they do respond to electromagnetic force, weak forces, and gravitational force. Types of lepton. Electron is a lepton, but why is a lepton? Basically, this is not good enough for me. There's only 6 types. No. I think there's 12 types, but it's just this is really annoying because it's not really because you got the anti-leptons, which are the these are at opposite, but opposite poles literally. Like if grav was if you're an alternating direction and grav is up, a lepton will be there. But I have to say now, so you get a lepton. A lepton is basically gravity. See, you have a plane. Like the floor, literally you're standing on. Anywhere you go on the sand, and gravity is pulling you down, and you're just in a still state. You are the lepton, but you're the lepton. You're measured by the lepton, because gravity will pull you down anyway, and that's what lepton is doing. It's measuring you, in that kind of sense. Basically, no matter how you rotate, how the system around you rotates, will be like you just basically someone looking at you and you're on the ground. You on the ground, lepton is nothingness off the ground. Basically, it's just gravity. It's gravity. But you can't have a gravity measurement in lepton. Basically, you have to basically you don't have a graviton. You have leptons that do this at the gravity. Basically, they are the equilibrium that keeps everything together. But if I'm working on something metaphysical, obviously it's something physical. I need a mass that's I can hold me, and that's what leptons are really doing. The anti-leptons are way to basically the leptons are the plane equivalent of it doesn't matter if you start from the 0, if you start from shear state of 0 between the chemical types of data, because leptons represent the 4 states to 1 state. So if you rotate 25 degrees, you get a bit of a view of electron, but you basically that means you're on an axis of electron, but you change your alteration. You're measuring something. You don't ever change your you don't ever change your direction because you are not the lepton. You are the measurement of the lepton. So you have to change how you look at it, what the literal angle you are at lepton. Like 25 degrees, 25 degrees, depending on your orientation already. And that's basically that's what basically you get 2 leptons to 1 2 left rotation to 1 full 360 turn. Right rotation. So you get you have to rotate twice for leptons to be in a mass. Again, absolutely. If you have an anti-lepton, you have what is a exerting mass, but that exerting mass is a waveform, and that's what the leptons are. I don't want to stay away from. It's like sending the mass of some kind of object to another person, and they can feel it, on the end of the world, because you're sending the actual physical information that's stored in leptons. that propagates in electrons as waves, because electrons don't have mass, because electrons are weightless. They don't have mass. They don't want to have mass. They don't, because the electron, muons, and tau. They do the things that are electrons, but you get the 1 over electrons. If this is a full electron, you get 1 over it. So that's basically nothing. As they can't observe, because how do you look at it? And that's what electrons want to be in that state. Doesn't matter how much the entropy is. Doesn't matter if you go to Mars. It reminds me of the Lorentz factor. Lorentz factor is like, I don't remember. But the reason to the observer, if you want to calculate them, they use the observer Lorentz factor, and that's what your 1 over the reference of a red wing to you, cyan, blue, that's what 1 over C, or 1 of the dash C, because if you are minus C, you are observing the inverse of the lepton. If you're cyan, and cyan, red green, green, blue, green, blue, and that'll be yellow. Sine yellow, sine, basically you get sine of yellow, which would be SOHCAHTOA bound, sine over cosine, secant, secant function. One of the secant functions you can calculate this kind of things based on the Lorentz factor of relativity of general relativity, which is Einstein's special relativity and the gravity I'm trying to glue together. But the system is just respective of the frame of reference, because it's just a big crunch, because everything implodes, so everything's moving far, nothing wants to be together, and the leptons just hold that state. They're still objects in the anti-state. So it doesn't matter. It doesn't mean means that you have all the matter, all the things in the physical form. But I think that's what it measures indirectly. Directly, because it's really good, but it contains all the properties of the electron. This is the electron. So you get electron. If you rotate twice, if you get 2 full electrons, you get a proton, and that's a proton. But the other trying to move on to like should be something like that. I don't even know them very well, but let's see what they are here. Name, symbol, electron. So electron, positive, negative. Basically, electron with a negative charge is negative 1, and a positive. We get a muon, which is a U. I don't know what this muon is, but this is a negative charge. But the negative charge of positive, that's a U on the moon. But I don't see that was a muon. I don't know what muon looks like. But these are charged antiparticles. So basically, they are charged because they are antiparticles, but they get a tau lepton. So you get the electron and the positron. So that's basically universal structure. Basically, the positron is positive, but its electron is positron. It's positron. Because you can get it. It's called a positron and an electron because they are both electrons, but they only do one thing. Electrons have no mass. They have mass. No, they have mass, but they're leptons because they don't want no mass. These things don't want to exist, just not be there. But you can measure its properties to tell you they exist. And that's what I'm saying. They want to be nothing instead of stay stillness. Just make sure everything's doing their job. Then they kind of what is energy? 40 equals to mass ratio. What is like people? Things observe you. They don't want to be changed. -1 electric charge, 2 lepton. Each lepton is a type of representation pair. Each lepton type is represented by a pair of particles called a weak doublet. One of the mass particles that bears the same name as the charge, like electron. The other, basically, we haven't observed the muon. I don't think that muon is important. I don't know. One of the mass charged particles that bears the same name, electron. Basically, I think everything can be monitored as electron, right? Because the electron is more than which neutrino, such as the electronic neutrino. So neutrino, the other, obviously, one of the mass of the charged particles that bears the same name as the electron is like an electron. The other is nearly mass neutron particle called a neutrino. A neutrino and electronic. Okay, yes, okay. This makes sense to me. So this is actually a factor. So this is the third one is very important because I think it's the only one I actually care about. So if you're doing electric field, you're working with electric field, you're working with an electronic system. So you want an electron only in that stable state. So the electrons will be things that can pass information via electrolytes. So electrons like if you have a noisy medium that can always kind of water. Water is not really propagated, so we can propagate them as waste. So you want to keep the electron in the neutrino state that have mass, because if the mass gets into the water, the system will blow up. Doesn't matter how you manage the core system. Neutrino has mass, and that will be the water. If you get dirt in the water, that's something that can some kind of impurity or ionic composition in the water that is that gives an ore. The water will blow. Will be contaminated by the neutron. Neutron will get to mass, so the system will be everything will be not what you want it to be. Start working for whatever system that more together anything that's want to be them. Okay. All six antiparticles, such as basically there's 6 antiparticles, but I'm saying there's 6 what? There are 12 of them. Oh, these are antiparticles. I think I'm saying what did I say? There are 12 each charge. There are 12 of them, but there's 6 and 6. So basically, you got a particle, you got an antiparticle. But that's 6 already because it's not 12. They're just one classification of them. So I'm saying there's 6 already here. But the antiparticle is just a measurement of the inverse system. So it can be in the 2-4 state topology. 4 times 6 is 12. No, 4 times 6 is 24. So basically it's 24. Yes, 12, but it's 12 already because 12 is one you can measure as mass or weight. But you get 24 in total. Sorry, not 12. But I'm the one question here. But I know you get the antron neutrino. But the electron antron is the inverse. All 6 pairs have a control antiparticle, such as positron or electron. All known charges of electrons have a single unit of negative charge or positive charge. All the neutrons have 0 electron. Yep. When passing around, usually the number of electrons is the same. Electrons are astronauts, muons. Yes, obviously, the principles that they do the interaction is just based on the quadratic system. If the current interaction, that means they're heterogeneous only, heterogeneous or homogeneous system. But they don't want to interact because they don't want to share the same state. No matter what they do, if they share the same state, we are moving towards they can't share the same state. But they want to want to resolve themselves because they're 2 different systems. But when partially required, this is the number of electrons. Electrons and electrons and what? Electrons and electronics and neutrinos. Muons and muon neutrinos remain the same. Yes, but for now, basically in this dimension we do have this kind of behavior. But if you get a neutrino. Yeah, it's something that's neutral. They can smash together, they can combine together, they can get the same. But the system is moving towards world. The universe is moving towards heterogeneous only. That's what I'm saying. There's no homogeneity. Basically, this combination of neutrinos not really needed to be the same allocated. You can get a spatial, but if you can, if you want to stabilize everything, the system will just move away to because of the big crunch theory and main provision. The principle known as conservation conservation of the number of electrons at different time. For example, electrons numbers are real numbers. Maybe something valid. For example, neutrino oscillation. Conservation of the same number of electrons of different types, of, for example, electronic numbers of muon numbers, may sometimes be violated. For example, neutrino. Yes, this is kind of a cause effect thing. Effect is like literally the cause of a system. So you can have a cause from another, but it doesn't have to be that way. So if you think of the effect as the thing that's actually happened, and you get something new, it makes more sense. So this it's like if you get an effect that affects you, it doesn't matter where you are. You have to do something to someone has to give. That's what I like to think about it. It's not like you want to do it. Someone has to give, and you have to get new isotropic stability in the ecosystem where the noise happen. Because you don't want to do that. So conservation of the number of electrons is just for example, electrons electronic numbers of muons. For example, neutrino oscillation. Neutrino. Basically, neutrinos have mass and wave, but the problem is the same thing. But the neutrinos are like they have mass because they have a neutral gram. They're neutrons because they are neutrons first. They want to stay neutral, but they oscillate because they are they have to handle the stuff. Basically, oscillation is like up down wave formation. But basically, you got a frequency, and then when something oscillates, it has some kind of vibration. But the vibration is in the medium of that thing. So that'll be affecting the leptons. And that's what it is. So the neutrons vibrate to spread out, to stop, to dissipate in the electron field, and the neutron field and the muons, and so they can have canonical state, share a canonical equilibrium, share a canonical. Something happens, but something happens because they have to share something, and if that something happens in the muons, it has to happen to the electrons, and the inverse one, everyone there. That's the neutrons oscillate at a quantum mechanical phenomenon where a neutrino created in specific lepton can later be measured to have a different time. Neutrino is a quantum mechanical phenomenon. This is the one understand it, but where a neutrino is created, when a specific can later measure to have a different time. Wait, what does that mean? Basically, this just makes sense to me. It just makes sense because basically, if you have neutrinos oscillate in quantum mechanics phenomenon. Yes, the way the quantum subatomic work. Listen, let me think of it. We get a less more model, but they oscillate. They have a ring. It's like if I implode, if I have a pen, something that's my dimension. Neutrino. If I have too much noise, if I have too much, think of it the information as noisy. Because if information is noisy, that means you have too much information, and I can't process it literally. And if I then if my environment is really noisy, if I can process it, I have another system, I can propagate it. I just dissipate it. I don't really need it because I don't hold that state. I don't need to hold that still state, and that's what neutrons do. When they oscillate, there's a quantum mechanics person for them because neutron is created. Because neutrons have to create it when to oscillate, and that'll be probably to some new information. And basically, it's biologically stable because it's based on entropy. So it's entropy in the nutshell. Like okay, it's just what it is. Basically, also it's quantum mechanics principle because when neutron is created, when it's politically needs to be measured, so of the neutron. Basically, the neutrinos don't change. They just propagate as waves. Sometimes they change, but sometimes they give. So if something they give, that means something else must change in the system. That's something a system of that heterogeneous only because that's the system it came from. Because it's just mixing and mango. So basically, it's meant to it's as do I have to lose or do I have to gain? It doesn't think about it. It just does it. That's what I'm saying. If you lose something, you have to gain something. So someone has to gain something, and that's basically what I'm saying. If someone gains something, someone has to lose something. But it's about the randomness, like a shuffling randomness. You just to stabilize the mechanical field that with all of them. Basically, oscillation is like the wave propagating in some kind of sequence, series of oscillations. Something goes basically. If you have an oscillation frequency, it goes up and down, but up and down is stable because it's like it's stable or side to side. It has some kind of frequency to it. It's like a snake shaking its tail. You get some kind of oscillation pattern. So basically, like can be read as noise. But you get too much signal in one system, to go out the other end. So you have too much information and still cannot handle it. Whether it's like a sound wave, you have to like stabilize itself, and that's letting go of some information, or let the formation in, but have a big effect on the other end. That's what I'm saying, guys. He has to do that to do one of those things, to stabilize the equilibrium of the other system that he go through. Dynamic presentation, no. Oh, look at 1 second. Oh, basically. Oh, it's done. I thought I'd be here for years. But we got the other one. Technology tech waiver. This is just like I don't even know what this website is. A slicer. Let me just find quantum field theory. Because I'm trying to that's too easy actually. So this one's a random crystal random field theory. Random crystal theory. Basically, I'm interested in crystal field theory because crystals are some of the structures that can stabilize. But I love crystals because they are there and they have stability. It's like fire. So it's like fire. If you have something that's fire, it's a crystal. Because fire to me is a crystal that implodes. So basically, it has to grow with the ice and the shape of some kind of topology to be safe to be. If a crystal has an endpoint, a sharp point, then it's fire to me. It's really dangerous and it's coming in red. So basically, that's what crystal is. It's like a dangerous substrate of fire because you don't, in some sense of the word. Crystal field theory. But I'm thinking of quantum field theory. My one. Bonding modern explained as the point of the transitional metal complex. Color, magnetism, structure, stability, and reactivity. Oh, can that be explained to valence bond? Covalent bond. Covalent. Valence bond theory. Central summation of CFT. I don't know. I come back to this later, but this is 5D opposite splitting. This is interesting. This is a D orbital. This is like a D. So get basically get XY. They get pull up as XY x squared plus minus y. This is kind of explained. This should be explained. But I don't know why it's explained. This is a metal citation. This is the integration problem. Electrostatic metal dx plus minus dy dx squared. Basically like oh wow. Basically I'm looking at this middle one. This is like a charge. This is just a change to this one. But I don't understand this graph. Basically this one looks at 6 charge distributed uniformly over the surface of a sphere, and this charge is allocated to the vertex of octahedron. Basically, this is tomographic, but this I'm working on. Basically, this is constant model too, but it's like a stable constant rate. Electrostatic attraction. Basically, the what I'm seeing in this graph is like you get a metal citation, m to the mass plus, but this mass plus is like literally what I'm saying is this one too. Basically, I don't look at this one too, the first one. I'm looking at the middle and the end because I don't know what this is what I'm trying to model. So I'm trying to infer what the system is, because I don't want to even look at what the metal citation was. But I think what I'm seeing is one something is progressing as a wave as a solitude, some kind of energy is dissipated in solitude, but they lose 6 electrons and they uniformly over the surface of the sphere of a crystal, and they lose 6 charges and the vertices of the hydrogen, and they get electrostatic attraction, which can be explained. Oh, so you get what? This is making sense now. So you get a crystal that can convert, they can hold electricity. The words. Well, it's interesting because they're not they're like d orbital. Basically, it's really interesting actually. The energy. I'll come back to this later, but I think I know what's happening here. But the d orbital splitting. That's my hypothesis. Like something that's a crystal that's holding a crystal structure holding a ionic composition that can not dissipate and can using electron attraction. Really, I think it's like ice that can grow that can hold water. But the ice is growing with the shape of the water. It's like an ice cube basically, but it's growing in a natural environment, which is a crystal. But the bonding is just a you get covalent bonding, and valence bonding theory, but you get covalent bonds of an ice crystal. But I can't remember what the term covalent means, and if someone can help me clear that up, I will help in the chat. Okay, guys, I've done what I want to do today. This next one I'm gonna do, but my hypothesis is just like that's my hypothesis. You get the complex octahedron. Those are the 8-bit one. You get this one question. It really is. They work on 8-bit access, because they are 8 byte access, not 8 because they are crystals. They have tomography to resolve, and that's area. Crystal first plane theory. Changing. This is really interesting, like guys. But I won't do it today. I need to just get it down. This is really interesting. Basically, okay, I'll go with. Let me just stop this video now.